Hey guys, welcome to your first lesson of this unit, and this unit is all about waves. So we're going to spend a lot of time this unit talking about energy. How does energy move from one place to another? So when you hear the word waves, we tend to think of things like water waves that we're really familiar with. But a wave is simply anything that moves energy. It could be sound energy. So a sound wave moves sound energy from one place to another. Could be light energy. Light waves move light energy from one place to another. So there's a lot of different things, a lot of different ideas we can talk about with waves. And so that's what this unit is all about. How do we move energy around from one place to another? So the first thing, and if you're looking at the screen, the first thing that we need to talk about is what waves actually are. There's so many different types of waves. So what do they all have in common? So a wave is an oscillation that travels from one place to another. Now, oscillation, also a huge word. Oscillation simply just means something that moves back and forth and back and forth. Like if you're swinging on a swing set or if you're playing with a yo-yo, those things move back and forth in a pattern. That's oscillation. So waves travel, they move energy back and forth in a certain pattern. Just like if you poke a floating ball, and I'm reading the second bullet here, if you poke a floating ball, it will oscillate up and down. And that oscillation spreads outward from where it started, just like this picture here. That is what the word oscillation means. So when you drop a ball into the water, some of the water is pushed aside and raised by the ball. So you can kind of see that energy being transferred from one place to another. You can see that energy moving. And there's kind of the little process of it down here in our chart if you want to pause for a second and look at that. So, another definition of wave, and this is the really important one here. A wave is a disturbance that carries energy through matter or space. It does not carry the matter itself. This is where it gets kind of tricky. So if you look at our graphic here, this bird sitting on the water, floating on the water, as the water waves travel, the bird just kind of moves up and down in that same spot. So does the water and the bird, the matter themselves are not actually moving. It's just the energy. And the energy disturbs them a little bit, but it does not carry matter. It doesn't carry things from one place to another. It just carries the energy. So while it can disturb the water and it can disturb the bird, the only thing actually traveling, starting at one point and ending at a completely different point, is the energy. And that's something that's going to come up over and over again. So I'm going to say it a couple of times. Waves carry energy. They do not carry matter from one place to another. Waves carry energy, not matter. So here we've got two different types of waves. And these different types of waves can then be broken down even further into more different types of waves. But these two categories are the big ones here. All waves, no matter what kind of wave it is, they can fit into one of these two categories. So we've got mechanical waves and we've got electromagnetic waves. And we're going to talk about both of these in depth. So a mechanical wave, the only difference is that they require a medium. Mechanical waves have to have a medium to travel through. So if you've taken an art class, a medium simply just means something that's already there that it's moving through. So mechanical waves have to have air molecules or water molecules or something like that to travel through. They cannot travel through empty space. So for example, sound waves are mechanical waves. Sound waves work by pushing energy through matter, through air, through water. If you went to outer space where there is no medium, there are no particles, there is no air, there is no water, sound waves wouldn't travel. They have to have a medium because they are mechanical waves. On the other hand, we've got electromagnetic waves in the other box on the right here. Electromagnetic waves can travel, they can move energy without a medium. They can travel through completely empty space. For example, light waves. So light from the sun can get to us because those light waves are electromagnetic. They do not require a medium. They don't have to have water or air or anything like that to travel through. And this is an idea that'll come pretty easily as we go through the unit. You'll get used to thinking about categories of waves and how they travel. So our next idea here is what causes waves? Why do they happen in the first place? What moves that energy from one place to another? So waves are created through vibrations when something vibrates. Most waves, not all waves. So a vibration is this repeated back and forth or up and down motion. You can see our graphic here, this little picture is a pendulum or Newton's cradle. I'm sure you've seen these before, where you have the metal balls and you let one swing and the energy moves through to the one on the other side. So these vibrations, sound waves work the same way. When you speak, you produce some sort of energy that causes the air in between you and the person who's listening to you to vibrate. And it's that vibration that moves the energy from one place to the other. So let's go into a little bit more depth about what I was talking about before, the two major huge categories of waves. So the first one is mechanical waves. These are waves that do require a medium. They cannot travel through empty space. So for example, sound waves, ocean water waves, earthquake waves, they all have to travel through something. Sound waves usually travel through air. Ocean waves obviously are traveling through water. Earthquake waves are traveling through rocks and dirt. They are not traveling through empty space because mechanical waves have to vibrate something. There has to be something there, some sort of particles for them to vibrate. Electromagnetic waves, on the other hand, don't necessarily need that. They can travel completely without a medium through 100% empty space. So visible light, like you see light from the sun, the only way it could get here is through empty space, right? Because it is an electromagnetic wave, it doesn't have to have that medium. Microwaves, radio waves, X-rays, these are all different types of radiation, different types of energy that can travel through a medium if there's a medium there, but they don't need one. They can also travel through 100% empty space. All right, so now that we've talked about the two major categories of waves, let's break waves down and talk about the different parts of a wave. So most waves share common parts. No matter what type of wave it is, they tend to have the same parts. So we've got, first of all, a crest and a trough. Here's some vocabulary words for you. You can think of a wave, as it says here, as a moving series of high points and low points. All right, so I want you to go ahead and kind of picture a water wave in your brain here. And here we've got a good picture of it. So you can think of a wave, as I just said, as a moving series of high points and low points. So if you picture that water wave in your mind, here's our picture. The crest is the very highest point, that top point. And we even say that. We say waves crest at this particular height, meaning that's as tall as they go. We also have low points in between these crests where it gets very, very low because waves kind of have this pattern to them. Those low points are called troughs. And if you'll follow my mouse here, right here in the center is kind of where the wave actually exists. The crest and the trough are kind of going around the medium middle part of the wave. Now, as we go through this, I want you to really be paying attention to these parts of the wave, these vocabulary words. We're going to get several more, and that's what we're going to be focusing on tomorrow, figuring out what waves look like in the different parts of waves. So far, we've got crests and troughs. Now let's talk about frequency. So waves also have a frequency. The frequency of a wave is the rate at which every point on the wave moves up and down. That sounds really complicated. It's not. Frequency just means how often does a wave occur? How often do we see the crest? How often do we see the trough? So for example, right here, we've got these up and down motions. So if I counted 1, 2, if you're following my mouse, that's the frequency of this wave. If they were closer together and we could fit more total waves in this picture, then its frequency would be higher. So when you're looking at a picture of a wave, the more crests you see, the higher the frequency, the more often that wave is occurring. Then we've got amplitude. The amplitude of a water wave is the maximum height the wave rises above the level surface. So again, talking about water waves, because they're very easy for us to picture in our mind, the amplitude is simply how tall does the wave get. You want to start at the center here, right in between the crests and the troughs, and measure all the way up to a crest, or you can measure all the way down to a trough. However high or however low it gets, that is the height of the wave. The higher a wave, the more amplitude it has. We also want to talk about wavelength, how long a wave is. So the wavelength is the distance from any point on a wave to the same point on the next cycle of the wave. So for example, the distance between one crest and the next crest, or the distance between one trough and another trough, or the distance between any random point and any other random point in the same spot on the next wave. I like to go from crest to crest or trough to trough just because that's easier. So let's go back to frequency, how often a wave occurs. The higher the frequency, the closer those waves are going to be together, right? They're happening more often. So if they're happening more often and they're closer together, you're going to end up with a pretty short wavelength. It's not going to be very far between one crest and another. Or if it is a long wavelength, if it is a big, big distance between one crest and another crest, then you've got a very, very low frequency. It's not happening very often. And there is just one more kind of graphic for you to look at if you want to pause it and take a second to kind of go over everything we just said. And the last thing I want to talk about before we're done, it's not too much longer, thanks for sticking with it, is a wave moves one wavelength in each cycle. So since a cycle takes one period, the speed of the wave is the wavelength divided by the period. So wavelength and frequency, how fast a wave is moving, is not actually how fast the water moves up and down, okay? Of the speed of a water wave is how fast it moves from one place to another, how fast it spreads. So it does have to do with wavelength. The longer the wavelength, the faster it can spread, right? It's covering more distance at a time. It also has to do with frequency. How many times in a given amount of time are those waves occurring? So the reason that we want to talk about the speed of waves, the faster a wave is moving, the faster it can get that energy from one spot to a totally different spot, the more powerful it is. So the last thing I want to leave you with is a little bit of math so that we can figure out exactly, we can actually do some calculations and figure out the speed of waves. So it's pretty simple here. The speed of a wave is the distance traveled divided by the time it takes, or wavelength divided by the period. And if you do some fancy calculations with that you don't need to know, if you'll look down here at the very, very bottom where my mouse is right now, okay, what you are seeing is wave speed equals frequency times wavelength. Wave speed equals frequency times wavelength. So we could actually, and we are going to do some of these tomorrow, we can do some problems where I give you the frequency of a wave or the wavelength of a wave, and you figure out the speed. How fast is that wave moving? And there you go. Wave speed equals frequency times wavelength. And the symbol for wavelength is kind of this weird upside down Y. It's a Greek letter. Just go with it. Speed equals frequency times wavelength. All right. That's it for this first lesson. So tomorrow, I want you to come in with a lot of that vocabulary kind of in your brain so we can start working with it. And the last thing I want to do is before you sign off for the night, I want you to turn in on Google Classroom. You can do it in a document. You can do a private reply, but make sure it's private so I know it's just you, a private reply. And what I want you to do is give me the definition of the word amplitude. The definition of the word amplitude. That's your vocabulary word for the day. And once you shoot me a Google Doc or reply to this assignment privately and hit turn in on Google Classroom, I will know that you've done this assignment and that you're ready to go for tomorrow. Okay? All right. Have a good day, guys. I will see you in class, ready to take all this information and do some fun stuff with it.